The third basic class is called compare. These operations will compare two values and set an indicator on the basis of the result of the compare. Now, most von Neumann machines will have a special set of bits inside the processor, which we call condition codes. Sometimes it's a special register called a status register or a condition register. But the idea is that these bits are set by the compare operations. So, for example, let's assume that there's a three one-bit condition codes. There are three one-bit condition codes called GT, EQ, and LT. And these will stand for greater than, equal to, and less than respectively. So if we have some operation like compare x, y, well, this means that we compare the contents of memory cell X to the contents of memory cell Y and then set the condition codes accordingly. So if we have this operation, we can set these three condition codes in some manner. So let's take a look at some possible conditions that we could have. So the first one will be something like con x greater than con y. Now, the notation con x just means the contents of memory address x. So what we're really saying here is the contents of memory address x is greater than the contents of memory address y. But to simplify, I'm just going to say con x and con y. So if con x is greater than con y, then what we would do is we would set the GT bit to 1, the EQ bit to 0, and the LT bit to 0. If we have something like con x equals con y, then the GT bit is 0, the EQ bit is 1 because this is equality, and the LT bit would be 0. And then if we have something like con x is less than con y, well, it means they're less than, so the GT bit would be 0, the EQ bit would be 0, but the LT bit would be 1 because this is a less than condition. The last basic class is called branch. Now, these operations alter the normal sequential flow of control. The normal mode of operation of a von Neumann machine is what we call sequential. So the idea is that after we finish completing the instruction at address I, the control unit would execute the instruction in address I plus 1. With branch instructions, though, they would actually disrupt this sequential mode of completing steps. So instead of just going one step at a time, these branch instructions will allow us to kind of jump around and go to different instructions. So it's not going to be sequential. So typically, determining whether to branch is based on the current settings of the condition codes. So a branch instruction is almost always going to proceed by either a compare instruction or some other instruction that sets the condition codes. So let's take a look at a couple of branch operations or branch instructions. So we'd have the jump X instruction. So this just simply means take the next instruction unconditionally from memory cell X, or just go to the instruction at memory cell X. We also have jump GTX. So here, if the GT indicator is a 1, we'll take the next instruction from memory cell X. Otherwise, we'll take the next instruction, the next sequential instruction. Now, we also have equivalent instructions, jump EQ and jump LT. So they work the same way, except we check if the EQ or the LT indicators are 1. And if so, then we will take go to the instruction at X. Otherwise, we'll just take the next sequential instruction. We also have jump GEX. So if the GT or EQ indicator is a 1, then we'll take the next instruction from the memory location X. Otherwise, we'll take the next instruction from the next sequential location. And then we also have similar instructions for jump LE and jump NEQ. So if they're less than or equal to or not equal to. And then finally, we have the halt instruction, which just simply stops the program execution. So we would not go on to the next instruction. So let's give an example of a high-level instruction and see how it would be done at the low level. So let's say we have something like this. If A is greater than B, then we're going to set C to the value of A. Otherwise, we're going to set A to the value of B plus C. So here is an example of how this could be laid out in our memory. Now, the address numbers are just kind of arbitrary. They may not be the actual addresses that we would use if we ran these instructions, but we're just going to go with it anyway. So we would start with instruction, the address 50, and then we'll run the instruction that's in there. And it says compare 100, 101, which means we're going to compare the contents at addresses 100 and 101, which, if you take a look here, address 100 has the value of A, and 101 has the value of B. So we're comparing A and B, and then we're going to set one of those bits, either the GT bits, or the EQ bit, or the LT bit. So the next instruction, 51, says jump GT 56, which means if A is in fact greater than B, then we're going to jump to instruction 56. So we would go all the way down to address 56, and here we have this instruction that says move 100, 102, which just simply means we're going to move A, or copy A, into C. So we would just, that means the same thing as setting C to the value of A. And then we would just move on to the rest of our program. Now let's say this is false. So if jump DT is false and we don't go to 56, we would go to the next instruction, which is at address 52. So we would do load 101, which means we're going to load the contents of address 101 into a register. So that means we're going to load B into a register. And then we would go to instruction 53. So we would go to the next instruction right here. Lovely arrow, there we go. And we would say add 102, which means add the contents at address 102 to the register as well. So that means we're going to add C to the register, which is the same thing as adding C to B. So now our sum is stored in some register. So then we would move to the next instruction at address 54, which says store 100. So we would store the contents of the register, which once again is our sum. We would store that at address 100, which is the value of A. So these three instructions at addresses 52, 53, and 54 are the same thing as saying set A to the value of B plus C. We then go to the next instruction right here, which says jump 57, which just means we're going to just skip the instruction address 56, and we're just going to go all the way to instruction 57, or I should say the instruction at address 57, and just carry on with the rest of our program. It is the task of the control unit to fetch and execute the instructions that we've been talking about. So to accomplish this task, the control unit relies on two special registers to fetch and execute instructions. So these are called the program counter, which we denote as PC, and the instruction register, which we denote as IR. Now the control unit also relies on what's called the instruction decoder circuit. The program counter would hold the address of the next instruction to be executed. So think of this as kind of like a pointer specifying which address in memory the control unit must go to in order to get the next instruction. So to get that instruction, the control unit sends the contents of the program counter to the MAR in memory and then executes the fetch operation that we described earlier. So for example, let's say our program counter holds 73. When the current instruction is done, the control unit is going to send 73 to the MAR, and then it's going to fetch the instruction at address 73. The program counter then would increment by 1 after every single fetch, because the normal mode of execution in a von Neumann machine is sequential, so we got to get the next instruction. So this program counter would just increase by 1 after each fetch, so then we would know to get the next instruction. The instruction register would hold a copy of the instruction fetched from memory. So the instruction register is going to hold both the opcode portion of the instruction, which is abbreviated as IR, op in this case, and then the address or addresses, which we abbreviate as IR with the address as a subscript. Now, to determine what instruction we use, or what instruction is in the instruction register, the opcode portion of the instruction register must be decoded using the instruction decoder. So this is the same type of decoder circuit that we've talked about before, and that was used in the construction of the memory unit. So here, the K bits of the opcode field of the instruction register are sent to the instruction decoder, which interprets them as a numerical value between 0 and 2 to the power k minus 1. And then exactly one of the 2 power k output lines of the decoder is set to a 1. Specifically, the output line whose identification number matches the operation code of this instruction.